All right, today we're diving into a totally mind-bending breakthrough in quantum computing. We're going to talk about how the secret to a massive leap forward was to first, on purpose, take a giant step backward. Sounds crazy, I know. Let's get right into it. I mean, just think about that for a second. It sounds completely backward, doesn't it? But a team of researchers, while tackling one of the toughest problems in computer science, stumbled upon this exact idea. And it might just be the secret to unlocking a whole new level of quantum power. So the problem they were wrestling with is called the low autocorrelation binary sequence problem, or LABS for short. Now that's a mouthful, but it's a famously difficult puzzle that actually has huge implications for the tech we all rely on every single day. Imagine you're designing a radar system. You send out a pulse and you wait for the echo. What you want is an incredibly sharp, clean echo, a perfect ping with absolutely no fuzzy noise or phantom signals cluttering it up. While the lab's problem is all about finding the perfect sequence of positive and negative pulses to create that ideal signal. To really get a feel for how hard this is, the researchers came up with a great analogy. They said, it's not like climbing a simple hill. No, it's like you're on a golf course from hell. A massive, mostly flat landscape, and the single perfect answer is hidden in one incredibly deep, narrow hole. You could search for ages and feel like you're making no progress at all. And wow, this table really shows you how quickly that golf course becomes an absolute monster. As the signal sequence gets just a little bit longer, the number of complex interactions you have to calculate it explodes. I mean, look at this. For a sequence of just 37 pulses, you're suddenly wrestling with over 34,000 of the most complicated four-part tangles. It is a total computational nightmare. So, how have we traditionally tried to solve this? Well, with some really clever algorithms for sure, but they all eventually hit a brick wall. And to understand why, let's think of the best classical approach as a kind of blindfolded golfer. The best classical algorithm is called mimetic taboo search. In our little golf story, it's like dropping thousands of golf balls all over the course, completely at random. Then, from where each ball lands, it does a really sophisticated local search. It even has a memory to avoid getting trapped in the same bad spots. But, and this is the key, its success ultimately comes down to pure luck. Just hoping that one of those random drops landed close to that one single, truly deep hole. And here's the wall. The time it takes to find the solution grows exponentially with the size of the problem. It scales at a rate of roughly 1.37 to the power of n. For anything but the smallest problems, this just becomes impossible. It doesn't matter how powerful your supercomputer is. Okay, so this is where quantum computing steps onto the scene. Instead of our blindfolded golfer, imagine bringing in a caddy who has some unbelievable intuition about the course. See, the quantum-enhanced approach doesn't just toss balls around randomly. It uses a quantum algorithm to kind of analyze the entire golf course all at once, and it generates way better starting points. This quantum caddy places the balls in a region that's already super close to the deepest valleys, which gives the classical search a massive head start. And here is the payoff. That scaling factor, it drops from 1.37 all the way down to 1.24. Now, that might not sound like a huge number, but because it's an exponent, the difference is absolutely astronomical. It means we can suddenly take on versions of this problem that were completely out of reach just moments before. So this was already a massive improvement, a real win. But then the researchers noticed something a little bit weird, something totally unexpected that was about to lead to an even bigger breakthrough. As they were digging through their data, they saw a pattern, a subtle clue in how the quantum algorithm was behaving. It was hinting at an even more powerful way to solve the puzzle, a path that nobody had even thought to look down before. So here's what they found. The most effective path the quantum algorithm was taking was always pushing right up against a boundary, a zero line in the math. It was almost like the algorithm wanted to cross that line, but something was just holding it back. And that led them to ask a really radical question. All the theory, all the textbooks said you run this algorithm between 0 and 1, but they thought, what if we just ignore that? What happens if we actually push the parameters into negative territory, a place you're really not supposed to go? And that right there was the breakthrough moment. By running the algorithm in reverse in this negative territory, they created a pre-annealing phase. Now, to bring it back to our analogy, it's like they figured out how to gently shake the entire golf course.
And this gentle shake uses the landscape's own structure to kind of settle the ball into an even better valley before the main search even kicks off. It's this tiny prep step that ends up changing the entire game.
So, what does this all mean for the future of computing? Well, this backward step is actually a giant leap forward in the race to achieve something called quantum supremacy. The holy grail in this whole field is finding the crossover point. And that's just the exact problem size where a quantum computer officially and for all time beats the best possible classical computer for that specific task. It's the moment quantum advantage becomes real. And that's what's so cool here. By making the quantum algorithm even more efficient with this negative lambda trick, that crossover point gets much, much closer. In other words, quantum wins sooner. This means we can actually prove a true quantum advantage on smaller, more achievable problems, ones we can run on the hardware we have today or very soon. Okay, so why does any of this matter beyond just making better radar systems? It's because this puzzle is basically a blueprint for a huge class of optimization challenges. The same kind of thinking could help us untangle global supply chains, build way better financial models, or even speed up the discovery of new drugs and materials. The potential impact here is absolutely enormous. Which really leaves us with a fascinating final thought. For the hardest, most complex puzzles we face, maybe the most direct path forward isn't a straight line at all. Maybe, just sometimes, to truly leap forward, you first have to have the courage to take a step back.